based on data that he had gathered from telescopes in the vicinity of Tucson. He got here and decided to broaden his horizons, and so he did his research exam project with Professor Soderberg on supernova. And there's a couple of nice papers that come out of that. But although the gravitational pull of exoplanets is relatively weak, it seemed to draw him back, and he couldn't avoid doing his thesis work on that topic. I think that, in a nutshell, if I was to summarize what first struck me about Jason's abilities, is that when he approached me about doing a project, I said, well, we've been thinking that maybe MIRF, which you'll hear about today, was really designed as a photometer, might actually also be a good machine for astrometry. I'm not sure if I told him at the time that actually we had tried to do it and failed. And then he came back relatively quickly, showing me the first parallax results for some of the stars. Jason, as a result, was really one of the first people to hold in his hands a catalog with a volume-limited sample of stars in the north, out to something like 25 parsecs. And by the end of my remarks, you'll find out why that's a very special sample to many of us here. So Jason's going to tell us today about his work really characterizing those very closest stars, how to determine their metallicities and their sizes, and their masses and their distances. I wanted to just use a couple minutes to tell you about a few things that he won't mention today, and that's some of the projects that are currently in progress. And there's really two scientific projects I wanted to tell you about. The first is that Jason is the principal investigator on a large Spitzer program, on a 100-hour program, to go after deeply interrogating one star where MIRF found a very interesting planet, a small rocky planet. But that particular planet was deeply flawed, Zach, because it's too hot. But we know that if we stare long enough at M dwarfs that have one planet, they typically have others. And so Jason actually only 2 weeks from now might know the answer. And if he's successful, that might actually be the first transiting habitable zone planet whose atmosphere could be spectroscopically interrogated. He's also worked a lot to improve the way that MIRF finds planets, and that is not something he's going to talk about today. But he used that to identify a really interesting candidate. We've been gathering follow-up radial velocities, and it also is looking promising and potentially habitable. He's been a successful teacher here. He taught in several different courses and got a certificate of distinction. Was that for Astronomy 100, which is the observational methods course, where we take the undergraduates out to use the telescopes in Arizona. And finally, I want to mention a few personal things. One is, Jason, I've really appreciated your interest in coffee roasting, showing up with lots of great coffee for our group meetings. And also, you and your partner are very adept fish keepers. Although I would be remiss if I didn't say that my 7-year-old daughter, Selena, would like to point out that was really just supposed to be for the sabbatical year. Okay. So, just as a final note, why I'm so excited about Jason's thesis is that I do believe that in the next 10 years, maybe in the next 5 years, humanity is going to get that first attempt to really look for life on other planets by studying the atmospheres of such planets, terrestrial planets, when they transit nearby stars. And it's virtually a guarantee that the first planet where we get an attempt to do that will transit one of the stars that Jason has characterized so very well for us and will tell us about today. Okay, so Jason, come on up and tell us about your work, please.
So, is this working? Chat. So thank you for that introduction, Dave. Before I start talking to you guys about the science that I've been doing while here, I would like to take a moment to acknowledge those that have impacted me and my work throughout my time here. And I'd like to begin by thanking my partner, Rachelle Baker, who's sitting right there. We moved out here from Tucson together, and in our big moving truck, as soon as we got off the highway, we were lost in Boston, which I'm sure is a familiar experience to many. We eventually found our way, but I would like to say that without you, I think I would still be lost today. And I don't think I would be standing here if it wasn't for your support. So thank you. I'd also like to thank Alicia Soderberg. As Dave mentioned, when I first came here, I worked with Alicia for a couple of years on supernovae, and she helped me understand a research field that I was not familiar with, and she taught me skills here that I had never learned before. So thanks to her, I've learned how to reduce radio observations and X-ray observations, and I really appreciate her mentorship. Of course, have to thank Dave for all the years of putting up with me and advising me. I'm sure it hasn't been easy. And when I came here, I had only done a handful of projects on individual planets, and you taught me to think deeper about things and to think on longer timescales about things, and to engage in projects that were much more fulfilling and had a much wider impact, and you've made me into the scientist that I've always hoped that I would be. And I owe that to you, and so thank you very much. Jonathan, who I had thought was not going to be here today because was just in Chile with the instruments that I'm going to be telling you about today, but your mentorship as well is extremely important to me, and when I come to you with a question, you usually have an answer before I'm even done asking it. And then by the time I get back to my office thinking that I finally understand all of these things, I forgot half of it. And so I would always have to come back, but you're willing to repeat everything, so it all worked out in the end. Or, well, it may all work out in the end. Of course, thank you to my committee for reading all of those pages that I sent you, with not enough time to read all of them. Especially thank you to Todd for flying all the way out here. And instead of warming up for your big race, you're sitting here and listening to some guy talk about things. I'm sure you would much rather be eating carbs than...
They're back there.
They're back there.
I know where they are.
And of course, this whole community here in this room, especially group members, both past and present, you guys have helped me throughout my work here. You've helped me with the science. When things haven't worked, you've offered to go out and buy me a beer, and when things have worked, you've offered to go out and buy me a beer. And so thank you for all of your support. And to the wider community here, I've had a great time here at Harvard these past 6 years, and it wouldn't have happened without all of you. So before you all look through and see if I remember to list you or not, I'm going to go ahead and change the slide. And I'm going to talk to you today not about supernovae, but I'm going to talk to you about the very nearby low-mass stars and what they mean to the planetary community and what they mean as interesting physical objects themselves. So when I came here in 2010, the Kepler mission, which we've heard so much about, had really only just begun studying the stars in the Milky Way and looking for signs of transiting planets around them. Kepler observed one field for several years, looking for these transiting planets and providing to us a statistical sample from which we can infer what other planets are out there. Is the Earth common? Is it not common? Really just the tip of the iceberg so we can begin understanding planets. And so when I arrived, you can see that Kepler was really just starting to take off. We had just started finding the first planet, these hot Jupiters, and we launched Kepler with this idea that we're just going to find a whole bunch of planets and it's going to be great. And indeed it was. It was really great. We found a whole bunch of planets, and armed with this information, we were able to ask ourselves, how common are planets? So I show here the number of planets per star with a period less than 50 days, with effective temperature rising from left to right. And so you can see that for the low mass planets, there's a sharp increase going towards lower effective temperature to cooler stars. And so we learned that maybe if we go a little bit further out here to the mid to late end dwarf regime, maybe there's just going to be a whole bunch of planets for us to discover and characterize. So Kepler taught us that not only are small planets common, but small planets are also common around M dwarfs. And the greatest thing about all of this is that M dwarfs are common. So I show here the census of objects within 10 parsecs. And over here, way on the left, this is the sun. So you can see that stars that are smaller than some of these red dwarfs really make up the bulk of objects in the Milky Way. And so this is an advantage for us because we want to be able to study the planets around these stars. We know that from Kepler that small planets are more common around small stars, and small stars are common. So I'm thinking now that perhaps there's so many planets that we can all have one ourselves. So this advantage also hints at this accessibility, that the planets around these stars are going to be immediately accessible to us and future instrumentation. So these stars, these nearby low-mass stars that host planets, will be the stars that we study with JWST and with the GMT in the future. And so the planets around these stars are going to be the best planets for us to study. And hinting back at this accessibility issue, I show here a 0.2 solar radius M dwarf. This figure is actually to scale, and you can see that the signature of a transiting planet, we get a much, much higher signal just by shrinking the star, because the signal goes as a ratio of the areas. So this, again, hints at this accessibility that the smaller the star is, the more accessible the planet is. And if you want to talk not just about the disk of the planet, but talk about the annulus of the atmosphere, you want to understand the constituents of the atmosphere, and maybe talk about the possibility of life making some of those constituents, then you really want to maximize this advantage as much as you possibly can. Similarly, if you want to characterize via radial velocity to measure the mass of the planet, you again win by going to smaller mass stars, just because the signal is much higher. So it's clear from these arguments that really, if we want to deeply understand the terrestrial planet population that we are going to be uncovering, we want to move to the M dwarfs. And so this advantage, however, is not without its challenges. And so part of the challenges is that these signals that I described depend on our characterization of the star. So the transit signal, the depth that we measure depends on the ratio of the radii, and the RV amplitude also depends on the stellar mass. So in order to understand the mass and radii of these planets, we have to understand the mass and radius of the host star. We only understand our planet as well as we understand the host star, because we are detecting the planet, understanding the planet through indirect means that take us through the host star. And so for my dissertation, I set out to characterize these stars, these nearby M dwarfs. And so I'm going to talk to you about how I used the MIRC dataset to obtain trigonometric distances to all of our target stars. I'm going to talk to you about how I calibrated the MIRC photometric system and why we needed to calibrate the MIRC photometric system to obtain a better optical magnitude for our target stars. I'm going to take a brief detour into galactic archaeology and how these M dwarfs can serve as a benchmark stellar sample in order to understand the M-dwarfs throughout the galaxy and why that might be useful. And finally, I'll bring it back down to the solar neighborhood, and I'll talk about this mass-radius relation in the low-mass regime. Most of my data and analysis use data from MIRF, and so I'm going to talk to you a little bit about what MIRF is, how we operate, and so that we can begin to understand these nearby stars. So MIRF consists of 2 arrays of 8 telescopes each, one at Mount Hopkins, Arizona, and one at CTIO in Chile. Each telescope is 40 centimeters in diameter, and we operate robotically with the assistance of Jonathan, who must be a robot, I'm convinced. And we target each star individually and monitor it throughout the night for signs of transiting planets. We use the technique of relative photometry, so we measure the brightness of our target stars relative to the other stars in the field, and this allows us to get to a millimeg precision, or approximately 0.1%. With this precision, since we're interested in the small rocky bodies, and the depth of a transit goes as RP over R star squared, we're really targeting the mid to late M-dwarfs, M4s and later. Because we want to get down to the signal-to-noise limit, we're limited by the number of photons. So this sets a brightness or a distance limit for our target stars. So we want to target the nearby ones. And the duration of a transit essentially sets the cadence of observations. Since on any individual night we don't want to miss a transit, and the transit duration is approximately an hour, we set our cadence to approximately 20 minutes. So with these constraints, that we're targeting the mid to late M-dwarfs in the solar neighborhood with a cadence of approximately 20 minutes, which really defines the MIRF data set. But when I say we want to target the mid to late M-dwarfs that are within 33 parsecs, how do we identify these stars? How do we know which ones we want to look at? And how do we essentially build our target list? So when I say M4 and later, we're really looking for stars that are red. If they're red, then they're cool, and we hope that they're M-dwarfs, but we don't want to be contaminated by red giant stars, so we need to find a way to figure out which ones are the close ones and which ones are not. And so we look for the ones that are moving fast, that have a high proper motion in the sky. Since proper motion is an angular measurement, the faster proper motion stars are more likely to be close to the Earth and the solar system. So one thing I should note is that when we say red, how do we get red? We're measuring the magnitude, the optical magnitude of these stars to see how red they are. And so one of the main problems was that many of these magnitudes came from photographic plates, and that these magnitudes are uncertain, and that could lead to errors in our distances. And so I illustrate that here. So here is the 10 parsec sample again, with the, here's basically an HR diagram. We have color on the x-axis and the absolute magnitudes of the distance corrected magnitude on the y-axis. Again, the sun is way up here. The sun is not a typical star. The bulk of the stars are low-mass stars in the Milky Way. And the mid to late M-dwarf regime is way down here. But in order to assess how red an object is, we need this color. And so with these photographic plates, many of these magnitudes have uncertainties on the order of 30% or higher. And so this leads to a error that translates directly into our assessment of the stellar parameters. So we don't actually know the stellar properties as well as we thought we did. This error in the stellar parameters then reflects directly into the planet properties we infer if we discover a transiting planet around one of these stars. And so what we want is a more precise way to obtain the mass of these stars, to really better assess which stars are the optimal targets to search for planets around. And so I show here a plot from Delfasa et al. 2000, who found that the mass of the star is correlated very nicely with the absolute K-band magnitude of the star. And so if you can get a distance measurement and a K-band magnitude measurement, you can estimate in the M-growth regime here a mass with approximately 10 to 15%. But the problem is, in order to get this absolute magnitude, you need a distance. And before my work with this trigonometric parallaxes, only 17% of the M-dwarfs in the nearby northern M-dwarfs had a trigonometric distance measurement. And so if we found a transiting planet in front of one of these stars, or orbiting around one of these stars, there was a 83% chance that we didn't know the distance to the star, and we didn't have a good assessment of its mass and its radius, and therefore we wouldn't have a good assessment of the mass and radius of the actual transiting planet itself. And so, if we want to be able to pick and prioritize which stars we want to look at and to understand the planets that we do find, we wanted to use the MIRF data to get better distances. So I show here a typical MIRF image. I'll note here that our pixel scale is 0.75 arcseconds per pixel. And so for a star that is at 10 parsecs away, the parallax signal is 1 over 10, or 0.1 arcseconds. So the star is going to be executing a motion well constrained within the size of any individual pixel. And so you can see immediately that we're going to have to be very careful if we want to do this correctly. And so the first thing we do is we recognize that, okay, MIRF is taking lots of data, it's taking data every night, taking data of the same stars every night, so we have a whole pile of data. So the first thing we recognize is that not all of this data, which is designed to do relative photometry, is going to be useful for astrometry. And so first thing you do is throw a whole bunch of it away. And so we do this with some simple criteria. We throw out data that has too high of a full width half max, so the atmosphere was not behaving very well that night, and so we throw out those data. We throw out data that show a high ellipticity, which occurs when it's very windy and the wind comes down and it rattles the telescope back and forth. And so we throw out data that show a high ellipticity, and we throw out data that were taken at too high of an air mass. I keep mentioning that these target M-dwarfs are red, they're very, very red, they're the lowest mass stars, they're the reddest things in the field, and luckily it's not cloudy outside, we can see that the sky is blue, and so the sky itself has these color-dependent effects, and so if we're looking through too much atmosphere, this may have an astrometric effect on our data, and so we throw out data that is taken at too high of an air mass. Once we've done that, the goal is to take all of the images that remain and come up with some model to line them up on top of each other so that any residual motion by the stars is believed to be real astrometric motion. And so we fit for this with a linear plate model, which I show here. So we transform each coordinate system via this model. This component here, C and F, you can recognize as we're just taking each plate and we're trying to line them up as best we can on top of each other. While this component here is actually just a generalized rotation matrix, where instead of all of these variables being arguments of the same individual angle, they're allowed to be free parameters, and this accounts for linear distortions such as changes in the plate scale and shearing on each individual frame. Once we've done this and tried to align all of these frames as best we can, we hope that the remaining motion is proper motion and parallax. So the actual true motion of the star in the sky as it orbits in the galaxy and moves at a velocity relative to that of the sun and solar system, and the parallax motion, which is what we're actually after. And so I show here the results for GJ1132, which is a planet that MIRF has discovered quite recently. And so you can see, based on the axis scale here, that we are well constrained within the size of an individual pixel, which is good, because that's what we expect. And while this might look like a fitted model, this is actually the recons measured parallax for this star. And so we can see that MIRF is able to reproduce the parallaxes that had been measured for stars before. But I mentioned that 17% of our stars had a measured parallax prior to this work, and so we can plot all of them up, which I show here. So you can see that on the x-axis I have the previously measured parallax from the literature, on the y-axis is the parallax measured from Mirth, and we're able to reproduce the parallaxes that have been measured before. These parallaxes are compiled from various sources. One of the main ones is the Yale Parallax Catalog, which is itself a assortment of various parallaxes from various groups. But I don't think that Dave would let me stand up here if I was just redoing other people's work to various precisions. And so the question we want to ask is the Mirth distance better than the photometric distance estimate that we had before? And so the answer is yes. So I show here now in blue are those same stars measured via literature parallaxes, and in red now is the parallaxes for all, or the photometric distances for all the rest of the stars. And you can see that the dispersion for the red data points is much higher, which means that, yes, we are actually much more precise in measuring the distances to these stars, which translates directly into our assessment of the stellar parameters. So now that we have a distance, we can revise our estimate of the mass because we can take the K-band magnitude measurement and our parallax and get an absolute K. And so I show here a histogram of the mass of our targets. In blue is what we believed it to be before this work, and in green is my new estimate of the mass. So you can see in blue that we tried to design Mirth to have this hard cutoff at 0.3 solar masses because we want to study the nearby low mass stars, and this was our best estimate for what the low mass population is. After we have obtained better distance estimates, we have this long tail of objects that were further away than we originally thought they were, which means they're brighter at K-band than we originally thought they were, which means that they are more massive than we originally thought they were. And it's these stars that we don't want to spend our precious observing time looking for planets around, because we're less sensitive to transiting planets around these stars. Another question you can ask is the Mirth sample complete? Do we have a complete target list? Or are we missing objects that we might want to be pointing our telescopes at? So I show here, I want to show you the number of stars that we have per unit volume as we move out in distance from the solar system. So I show here a R-cubed line, a black line, going out in distance, and a cumulative histogram of the number of stars. And so you can see that once we start falling short of this black line, then there's targets here that we are potentially missing. And so I find that in the northern hemisphere, we're basically complete out to a distance of around 25 parsecs. You can ask, how does this stack up when you try to separate these out into different masses? So if I ask for the bluer and the redder objects, how complete are we? You can see that for the more massive N-ghosts in the sample, that we're complete out to a distance of around 25 parsecs, but for the very reddest stars, the very lowest mass stars, which may potentially be the most valuable stars, we start falling off around 18 or so parsecs. Now, I'm going to talk to you about calibrating the Mirth photometry, because you saw in that previous plot that we were separating things out by color, and I alluded to before that some of the optical magnitude measurements were taken from photographic plates that were not as well constrained, that have higher error bars, and so we realized that Mirth itself is an optical survey, so if we can just calibrate Mirth itself, we can replace some of these magnitudes, which may be quite uncertain, with one that's better. And so, Jonathan Irwin had the foresight to begin each observing night by observing some Landolt standard fields. These fields are stars that are very well characterized, very well studied, and we believe we know the actual true amount of energy we are receiving from these objects. And so we have Landau fields every night, and we take our target images every night, and so we can combine these in just the right way. We can measure the Merth bandpass optical magnitude for these stars. And so we use the following model. We say the Merth magnitude is some function of fluxes, flux over time, where we convert to magnitudes via logarithmic term, or by taking the log. We have to correct now for the atmosphere, so we correct linearly with the air mass because the atmosphere extincts some of the light as it's coming down to our telescope. And we also have to correct for the air mass times the color of the star. Because again, we're interested in the reddest star in the field, and so because the sky is blue, and we have to correct for the fact that our reference stars are going to be differentially more extincted than our target stars. And finally, we have to put the whole magnitude system on a 0 point, which is defined essentially by the Landau standard stars themselves. I'll point out that the Merth magnitude and the color that we use here to correct for our photometry is the Merth minus K color. And so the Merth magnitude appears on both sides of this equation, but that doesn't have a significant effect on our results, and Merth minus K color is an effective color to use for these corrections. So I show here the residuals for this model on a particular night. You can see the air here is big. We have multiple peaks indicating that the atmosphere on that individual night was changing significantly. And so while this data may be useful for relative photometry because you're looking through the same patch of atmosphere, nights that look like this are not photometric nights. And so we take nights like this and we throw them away. On a better night, one that is photometric, our residuals look more like this. If I blow this up a little bit, you can see that we have a nice well-defined peak, and our residuals now are on the order of 1%. So on a photometric night, we're able to measure the magnitude of these stars with approximately 1% precision. So this is great. We find all the nights that look like this. We put them all together and say, okay, now we have a bunch of measurements of the magnitude, the true absolute magnitude of these stars. So nights like this get the photometric stamp of approval. And so if we take our whole pile of nights for just a random individual target, you can see we observed it over multiple observing seasons, and that the stability is approximately 1 to 2%. But we have this for all of the Merth targets. So if I take the parallaxes that I just showed you previously to get an absolute K-band magnitude, use this photometry now that I hope I've convinced you is precise in order to obtain a color measurement for these stars. And I take a metallicity measurement from Newton et al., which found that the sodium line in the K-band is a metallicity indicator for these stars. I can show you the following plot. So I'll preface this by saying the thing I like most about this plot is that there's no models here, there's no theory here, this is all just data. And so on the y-axis here is the absolute K-band magnitude. On the x-axis is color, so over here is more blue stars, and as I move over here, we go to redder and redder colors, and I've colored each data point by the equivalent width of this sodium line. So you can see that the more metal poor stars, the stars with a lower sodium equivalent width, are bluer than stars that have a higher equivalent width. Remember that the absolute K-band magnitude is a mass indicator. So what we're saying is that stars that are at approximately the same mass get redder as you add more metals to them. And so what we've done here now is we can calibrate a metallicity relation. So if I now switch from sodium equivalent width to a metallicity measurement for these stars, this metallicity comes from the spectroscopic relation, which is itself calibrated off of main sequence FGK star with M star pairs. And I plot here in black a solar metallicity main sequence. We've now calibrated a luminosity color metallicity relation for these stars. So the natural question is, well, how good did we do? So I show here the residuals of this interpolation as a function of color and as a function of absolute K-band magnitude. You can see that we don't have significant structure here, and we have an RMS of approximately 0.1 dex. Using a distance and a color measurement alone, we're able to estimate the mass, or estimate the metallicity of these stars with a precision of practically 0.1 dex. So now we can do this for all of the stars. So now I've plotted all the stars for which we've obtained a trigonometric parallax and a Earth minus k color. And so you can see we've measured the metallicity for all of these nearby northern hemisphere M dwarfs with this precision. You can then ask yourself, what does the metallicity distribution of these stars look like? Do the M dwarfs look like the nearby G dwarfs? So if I restrict myself to this volume-limited sample that I described at the end of that parallax work, this is a histogram of the metallicities in the solar neighborhood. So you can see this black line is the median value. So the typical M dwarf metallicity is solar metallicity. And the distribution at the low metallicity end is very similar to the nearby G dwarfs. And so essentially, we can conclude that the M dwarfs in the solar neighborhood are derived from the same star formation history as the nearby G dwarfs. And this brings me to this next topic here, that these M dwarfs now, if we have this metallicity distribution on the nearby M dwarfs, and they tell us something about the chemical enrichment and star formation history of the galaxy. If we can just do this for all of the M dwarfs that we know, then perhaps these can be a useful tool to study the galaxy itself. And so I'm going to talk to you about galactic archaeology. If I go back to this plot, you may be thinking, well, there's kind of a problem that you kind of need a distance, not just to the nearby ones, but to all the M dwarfs you ever want to use for this, and you kind of need a Mirth magnitude. And so Mirth isn't a standard bandpass, and we're not going to have distances to many of these stars, and I'll explain to you why. You may be thinking that, oh, Gaia's up there, Gaia's going to measure the distances to everything, you don't have to worry about it, because Gaia. But if I show the Milky Way here with the sun here, Gaia is going to detect things down to 20th magnitude in the Gaia passband. The Gaia magnitude system is an optical magnitude, and red stars, these M dwarfs, are dim in the optical. So Gaia is actually only going to get us out to approximately 500 parsecs for these types of stars. The galactic center is 8.5 kiloparsecs away from us, and so we're not actually going to have a distance to these stars. And so we're going to have to find something different than an absolute magnitude measurement if we want to use M dwarfs as tools to study the galaxy. In terms of finding a magnitude, an optical magnitude, LSST is set to begin operations shortly, kind of shortly. And it's going to go to a much deeper magnitude limit. It's going to detect M dwarfs out to 30 kiloparsecs away. And people are talking about detecting M dwarfs in the Magellanic Cloud. So essentially, we're going to be detecting M dwarfs throughout the galaxy. So the magnitudes are covered, but we need to find this replacement for distance if we want to characterize M dwarfs in the galaxy and use them as probes of galactic structure. So the question we asked ourselves is, well, can we use Sloan colors? LSST is going to use the Sloan bandpass, and so if we can just calibrate a relation using what we're going to have, then maybe this can work. And so this has been done before to some extent, so I show here a plot from West et al. Of G minus R and R minus Z colors for M dwarfs in the SDSS survey. These points are colored by spectroscopic line ratios that are believed to be metallicity indicators for these types of stars. And you can see that the metal poor stars tend to pull themselves away from the metal-rich population. And okay, so that works if we can measure G, R, and Z magnitude for these stars. But I'm going to briefly get pedantic with you here and talk to you about the prime filter system and the unprimed filter system. So the prime filter system is defined by the United States Naval Observatory, which measured the GRIZ magnitudes to a series of now standard stars that define this system. SDSS originally was going to be on the prime system, but when they put their filters into vacuum, the red cutoff for these filters shifted in wavelength by approximately 2% bluewards. So I showed here as dashed lines the prime filter system, and as solid lines the SDSS filter system. And you can see that, yes, there is indeed this shift. And it looks small. And indeed, SDSS says that these differences are subtle, and they can be transformed with simple linear transformations, but cannot be so transformed for very cool objects, objects with complex spectrum. An M dwarf is a cool object with a complex spectrum. So this is a Pickles M4 template spectrum, and you can see structure essentially everywhere. You can see deep troughs and lines and molecular bandpasses, and so the question is, well, if I overlaid all of these filters, is this going to hurt us? You can see that, especially in the R band here, that this cutoff is kind of sandwiched right between two very sharp features, and if we just shift this a little bit, is that going to affect our measurement? Is this going to affect the type of relations we can use? And so this is what we've set out to investigate. And so the question is, can we use GRIZ photometry to characterize M dwarfs? And so over the course of 16 photometric nights, we took observations of these standard stars that define the prime system, and as well as target M dwarfs. We used this same model that I described to you previously, but now instead of a mirth minus K color, we're going to be using a G and an I magnitude. The 48 here is because this is the 48-inch telescope on Mount Hopkins. So we're trying to calibrate the Sloan magnitude system with the Sloan filters available on Mount Hopkins for the 48-inch. And so one other detail that I need to mention here is that here are all of the GRIZ prime system standard stars. And this is a histogram of their G minus I color. In blue are these standard stars, and our green are the measurements for all of our target M dwarfs. So you can see that there's very little overlap here, that the red end for this magnitude system is not actually very well defined. And so what we're almost in a sense doing here is we're pinning down what actually happens in the red end for this system, because we actually lack the standard stars as a definition to guide us. But once we've reduced our data, we have now a magnitude, a G, R, I, and a Z magnitude for M dwarfs in the solar neighborhood that have a spectroscopically determined metallicity. So hopefully we have all the ingredients that we need, and if we think really hard and make enough plots, maybe something will pop up. And so I show here now the same plot that was in West et al. At G minus R versus R minus Z color. And if you remember that the metal core stars tended to move up and to the left in this diagram, but you see here when I color the points by their spectroscopic metallicity, we see kind of blue dots everywhere. So in fact, if I compare the two, it seems like that the photometric metallicity relation from SDSS does not really work for more Sloan-like filters, ones that haven't been shifted. And I alluded to this before, but we believe it's because the slight changes in the filter between the two systems really makes a difference for stars that have complex spectra, where you have lines and features and things going up and down everywhere, that this doesn't actually provide the precision that we may otherwise need. And so we can conclude that at least the SDSS broadband relations do not translate well to Sloan filter sets. But what if we retreat from this goal and go back to our absolute magnitude relations? So if I show here now the absolute k-band magnitude and the absolute I-band magnitude as a function of g minus I, we begin to see some separation in the metallicity of these stars as a function of color. And the precision of these measurements is approximately 0.13 dex. But what we really want is to do this with just color. We're not going to have distances to most of these stars, so can we get away with just color? And can we get away with just the colors that LSST is going to provide for us? And so I show here G minus I versus I minus Z for these same stars with a best fit main sequence. And you can see that it actually doesn't do very well. There's blue points pretty much everywhere here. We're not really able to get it to work. And in fact, the standard deviation is about 0.16 dex, but the standard deviation of our metallicities themselves is not much greater than this. It's about 0.19 dex. So we're not actually measuring the metallicity very well using these colors. So we think that there is actually no Sloan-only color combination that serves as an effective metallicity indicator for these stars, for the M dwarfs. But if we move to the near infrared, so I show here now G minus I versus I minus K, now you can see that the blue metal poor stars are all falling to the left and the reddest stars are falling to the right. So perhaps if we just relax this constraint that we're trying to do this only in optical in this narrow region and move to the infrared, now we can do it. And the precision of this relation is about 0.1 dex, which is comparable to the precision that we can get from the spectroscopy measurements themselves. So great. We can get a color-color metallicity relation if we have a G magnitude, an I magnitude, and a K-band magnitude measurement. LSST is going to provide us G and I, but where are we going to get K-band magnitudes for these stars? The VISTA hemisphere survey is actually measuring the southern sky, the southern hemisphere sky, which will overlap with LSST, and it's going to be measuring the K-band magnitudes of these objects. It doesn't go as deep as LSST, but like I keep saying, these M dwarfs are very red stars, so you don't have to go as deep in order to detect them because they're red, and so you manage to still pick them up anyway. And so for the LSST M dwarfs that we're going to begin uncovering, most of these will have VISTA data. And so it's going to be a question of source matching and source overlap between the two data sets. And if you can match the LSST M dwarfs with the VISTA source detections, then we will be able to measure the metallicity of these M dwarfs with a precision sufficient to really start probing the chemical evolution of the galaxy itself and the M dwarfs in the galaxy. I've sort of gotten a little bit sidetracked here talking about galactic archaeology, but I'm going to actually bring us back to the solar neighborhood, to the inner 30 parsecs, and talk to you about mass and radius of these stars. And so I've talked to you a lot about mass, about how do we get mass, do we get it from the distance and the magnitudes, do we get a color relation, but Earth is looking for planetary transits. And the transit is not sensitive to mass, it's sensitive to the radius. We're detecting the radius via the depth. So how do we get from a mass to a radius? Can we use stellar models? Can we just say, well, if we know the mass, we just go look in the table and say, oh, okay, here's the radius. The problem is that in order to measure this radius, I show here the mass and radius for low mass stars. And here is a stellar model, and here are actual stars down in this regime. And you can see that they all lie above this line. So if we only naively just say, well, I'm not going to think about actual stars, I'm going to think about the stars in my computer, we're actually going to underestimate the radius, and therefore we're going to underestimate the planet mass. And if we're interested in such things as, well, do planets transition from a rocky regime to a gassy, volatile, rich regime at some radius? Gotta know the radius of the star in order to do that. and if we're underestimating it, we could run into systematic issues. So I show now the fractional error in the stellar models as a function of math. And you can see that these errors are not insignificant. We're talking on the order here as high as 10% error just from using the stellar models. And so really we want to do better than this, but you also notice the lack of data here, that we don't have a lot of accurate or precise radius measurements of these nearby low mass stars. And so if we want to start disentangling effects, well, are they inflated because they're active? Are they inflated because some have more metals and some have less metals? Every time we start talking about, well, is it this or that, and we add another variable, we need more data in order to actually figure that out. And so while I was here, we began construction of a new array, the Merth South array at CTIO, which I told you about before, and we began operations 2014. So when I started, it sort of looked like this, but now it looks a lot better. And thank you to Jonathan for taking such an amazing photo here. And so I'm going to talk to you about the eclipsing system LP661-13. This object was actually discovered on the second night of commissioning observations. And I show here some data where Merth was monitoring the star for potential transit. So it takes data every 20 minutes, which you can see here. But then right here, it recognized in real time that, oh, something had happened. The star is dimmer than we thought it would be. And while Merth South is ostensibly, we're looking for transiting planets, really what we're looking for is for the flux to go down. And so stars can block light just as well as planets can, and actually they're much more effective at blocking light. And so Merth is actually also able to discover eclipsing binary systems to characterize the mass and radius of these stars. So Merth noticed that, oh, something had happened here, and so instead of continuing this monitoring cadence, we parked on this star and monitored it as we watched the eclipse end, and then once the eclipse had ended and the observatory decided, oh, okay, everything's back to normal now, it resumed this lower cadence observation method. And so after discovering this object, we observed it for 2 seasons. We collected 22 eclipses, which I show here. So on the left is the primary eclipse. All the data is for all the primary eclipses, and on the right are all the secondary eclipses. And we also took 8 epochs of high precision RB spectroscopy using the TRACE instrument at Mount Hopkins. And I show here the radial velocity orbit. In blue is the primary star, and in red is the secondary component. And so with the Merth eclipses, we're able to get the radii of these stars. And with the trace spectra, we're able to get the masses. So we have a mass and a radius, and a whole bunch of other things go into that, which I'm not going to tell you about: star spots, rotation, systematics. But at the end of the day, if you have a double-line eclipsing binary system, you can get observational constraints on the fundamental properties of these stars. So if I measure now the mass and radii of each component, you see that we have a 0.3 and a 0.2 solar mass star with a 0.32 and a 0.22 solar radius radii. And with the wealth of data that we have, we're actually able to measure these parameters with approximately 2% precision. So now we can place these objects on the mass-radius relation. So in dark blue are these 2 stars of this system, and these red data points are other eclipsing binaries that have been discovered and characterized by other groups. This black line is a stellar model at solar metallicity from Brath et al. 2015. So this is the essentially the latest and greatest stellar model, but you can see that basically all of these data points lie above this line. And so we still have this issue where the models aren't quite measuring the radii of these stars accurately. Excuse me. These stars are fully convective, so it's not terribly surprising that we have some issues with the modeling. These stars are not like the sun. They're fully convective. They're physically different, than the sun, which has an outer convective envelope, but energy in the interior is transported radiatively. And so with these new systems, we're now beginning to discover enough systems that we can start asking questions of the data. And so it's my hope that in the future that we're able to make these models better. We're going to hopefully be able to understand, well, is it the active stars that are principally the problem? Is it the metal rich stars? Does metallicity affect the radius? These are open questions that I am not going to try to answer with because I don't have them. So I've talked to you today about the work I've been doing studying these low mass stars, these stars that are within approximately 33 parsecs of the sun. These are the stars that are the best stars for studying planets. They're close, they're small, they're bright, and the planets that we eventually uncover around these stars are going to be the planets that JWST and the ELTs will study. And so it's my hope that one day, hopefully soon, we'll find a habitable planet transiting one of these stars. But in order to understand that planet fully, we need to really understand the stars. And so my work has focused on fundamentally understanding the nearby stars in the solar neighborhood. And what I mean by that is that we've measured the distances to these stars. Many of them we've measured the distance to for the very first time. We've measured their intrinsic luminosity. We've determined their metal content. And we've provided better estimates of their masses and radii, which will, in effect, provide us better estimates of the masses and radii of whatever else may be hiding in those systems. And I've made an effort to transform the nearby M-dwarfs into a benchmark stellar sample that hopefully other people here and elsewhere can use as tools to understand the chemical evolution of the galaxy. And so I'm going to leave you here with a map of the stars in the northern hemisphere, colored by their metallicity, with the sun in the center. And one of these stars probably hosts a transiting planet. We don't know which one it is, but we may soon. And we're going to want to know as much information about that star as possible. And it's been my goal to provide that information. So I'm going to leave you with that thought and display to you the work that I've been doing here over my time. Thank you.
Hey, great. Okay, questions from the audience. Peter?
So, Jason, so you've done a great job of getting these trigonometric parallaxes for a large sample. Now, the vast majority of those you're not going to detect planets around, and the ones that you will, are those parallaxes good enough that they overcome, the distance uncertainty to the point where other things take over as systematic, or will you then want to go back to those stars specifically and get even more precise parallaxes?
So Gaia will, I know I told you that Gaia's not going to do this, not going to do that, but for these stars, these very nearby stars that we're going to care about for the purposes of planet characterization, by the time we are getting to that point where we find the planet, we're like, yes, this is the one. Yes, get JWST up there now. And Gaia will provide a distance to those stars much better than any ground-based observatory will be able to do.
Although I have told Jason that he need not apologize for doing it at 1,000th the cost and 3 years earlier.
Yeah.
Only 1,000?
Yeah, probably. Well,
I'm very
it depends how you count Labor Day.
So then, given that Gaia is on the horizon and we'll do this a little bit better,
Yeah.
is there any motivation to do this with the Mirth South data, to measure parallaxes with Mirth South?
So if we detect a planet before Gaia's data release, Gaia is releasing data in August, but it will not be releasing parallaxes this August. It will only be releasing proper motions, and even then, I think only for a subset of their stars. So we still have a little bit of time to wait, and in that time, we may discover a planet, and we'll want to characterize it immediately. So in that sense, the Merz-South astrometry is ready to go now. Basically, I can hit enter and I can tell you, if we have data for the star, I can tell you its distance. Another benefit of having data from Earth is that, yes, it will be lower precision, but for some of these stars, we may see astrometric signals from Gaia, from orbiting companions at much longer periods, and Gaia is a mission, it's going to end, it's going to have a finite time baseline, and we will have data at lower precision preceding that in time. And so we can use Mirth ostensibly to extend the time baseline and measure these longer period systems at a lower precision, but we can then talk about dynamical masses and all sorts of things. So ground-based astrometry doesn't end and die with Gaia. There will still be things to do, and hopefully Mirth can be useful in that sense.
Ramesh.
So, do you have any high proper motion halo stars in the sun?
We have Bernard's star off the top of my head.
I try to remember the plot you showed. I didn't see anything, any real outliers in proper motion.
So I did not show any of the proper motions of any of our stars. So we didn't.
You showed only the parallax.
Yeah, so that was purely the parallax signal. But we do have stars that show very high proper motion. Bernard's star is the classical example.
Okay. Actually, one other question.
Absolutely.
Yes.
In your parallax comparison, there was one outlier point. tiny error bars sitting way off. So did the other guys make a mistake?
So I dangled that out there as bait.
Yeah. So who are these other guys? They must have made a mistake.
So that plot used the previous literature estimate that had the lowest reported error bar. There is one other measurement for that star at a higher error bar, which is the same as the measurement that we measure. So I'm not going to point fingers. But, I mean, those guys probably messed up with it.
You're not going to tell us who they are.
I don't quite remember. I think I know, but let's not.
So it's not someone very famous.
Charles, yeah.
Just briefly, where did you get the K magnitudes from? You maybe said that.
So the K magnitudes came from true mass. So this is ongoing right now, but I don't know what the status of their data release is. But basically, all of our target stars are very, very close to the sun, so they're all in 2 mass.
Okay. And Baraf et al., are they commenting on these clear systematic errors in their mass-radius relationship?
Many people comment on systematic
They're
errors.
models, right?
Yeah, so essentially what we have here is we go to lower masses, we're transitioning from into this fully convective regime. And so we can expect there to be a discontinuity here because we're transitioning physically and structurally to an entirely different type of beast. So we talk about M stars as like M0 to M9, and they span a large range in mass, and their structure from M0 to M9 changes radically. So it's actually, M-dwarfs have kind of been this like trash pile while all the red low mass stuff is in M-dwarf. But really, by the time you get to the end of the sequence there's radically different changes, and so you can maybe expect that to be reflected in the overall physical patterns.
Because they seem to do better at the very low mass end.
Mm-hmm. So yeah, so the problem is like really at this transition where everything's going crazy, and maybe, like, is it magnetic fields in the star that's kind of like smearing out these transitions and inflating the stars, and metallicity is really an open question. And so yeah, once we get down into this, like, everything is fully convective, this is the way it is, it's much easier than something that's sort of like on this boundary.
Initially, I think that theorists hoped that the discrepancies we could only measure it for the binaries, but because you had a close binary, maybe that was doing something like torquing the star or inducing magnetic activity. But But Mirth and Kepler and other projects have really shown that's not the case. Even long period binaries seem to be discrete. And yeah.
So you were talking about the photometry and using the combination of Vista and LSST. One thing you didn't mention is LSST will have a wideband filter that goes slightly beyond 1 micron. Do you think that will be useful? I mean, it's not easy to calibrate, but
Right.
would that be useful?
Potentially. I mean, what we've demonstrated is that if you want to do this, you need to have one filter that's pushing out in the infrared. Whether wideband will be sufficient for this, I can't say, because we didn't have any wideband measurements for any of these stars. One thing that would be useful is to use the 48-inch now to take deep pointings that will overlap with eventual LSST pointings so that we can calibrate the two systems relative to each other, so that we can maybe start investigating, well, can we get away with wideband or not? But I don't actually have an answer to that question. Redder is better, but is red good? Is that red good enough? Is sort of iffy.
So you have these very nice metallicity measurements for your end dwarfs, and ultimately that's going to spread throughout the galaxy. Do you expect the exoplanet population to in any way trace your end dwarf metallicity for the sea stars? Or not?
So whether a planet metallicity correlation exists for low mass planets is an open question. If you would have asked a few years ago when we only had hot Jupiters, it was clear that high mass planets need high metallicity in order to form so that they can accrete enough to start forming accreting gas and becoming big and puffy. Since we've discovered lower mass planets and we're pushing more into this like rocky terrestrial regime, it's sort of unclear whether they care at all about metallicity. Certainly, if you have more metallicity, you can form planets earlier, and maybe you're more likely to get GJ1214 type planets that are nice and puffy. So maybe there's a sweet spot where you want to have enough metals to form planets, but you don't want to have too many metals because then everything gets big and puffy, and then you can't form life on these planets anymore. So maybe there's a lower metallicity is a sweet spot where you can form planets, but they don't form fast enough so that the gas in the disk dissipates, and they stay rocky. And there's a lot of papers out there that sort of argue this back and forth. Well, low mass, in order to form planets you need metallicity, and so we need to go after high metallicity stuff. And some say, well, low mass planets don't really care. You just gotta have a star and they're good. And so this is really, once we start finding planets around these stars have metallicity. So I advocate that the best thing to do is to keep the theorists honest and wait for the data to come in.
I believe some members of your committee have strong opinions about this.
Yes, but I'm keeping my mouth closed.
Any other questions? John?
I think there was a question.
Oh, Andrew.
Yeah, if you go a slide back, is the sun in a hole?
Let's see if I can do this. So, in the sense that the very, very close stars, so first of all, there's a couple of things happening here. This is a plot that's linear in radius, and so actually, since we're smashing the entire volume onto a plane, we actually there's less volume in this area anyways. But also, some of the very, very nearby stars that are also more massive than the more massive target list N are too bright for us. We'll saturate on them, and so we actually don't observe them. But basically, there's like this inner area basically is a smaller volume, so I'm kind of deceiving you a little bit there. And we've thrown out some of these stars because they're just really not good targets.
If only there was a definitive catalog of the 10 parsec sample.
It
Professor
exists.
Henry.
Would you like to see the draft?
Oh.
It's right in here. The published version.
Good. Okay. This is not the end. We will adjourn in a moment, and then the committee will reconvene at 2.
2:30.
2:30?
2:30.
Really?
Okay. Because should the defense be successful, then around 4:30, there might be some kind of a tasting of
Sparkling wines.
sparkling wines.
In this room.
In this room. But for the moment, let us thank Mr. Dittmann again.
Yes.
Word on the street.
What?
Did you change